Good morning guys, welcome back to my YouTube channel. Welcome back to King Solomon Holiday Classes. My name is Stephen Ben. Today guys, I want us to solve this simple beam. This is a simple beam on two simple support and a point load. So guys, stay tuned. Please don't forget to subscribe, like the videos, comment and share to your fellow colleagues. So guys, today we are going to solve a simple beam on two simple support and having a point load. So guys, let's start. So guys, to start with this type of beam, you start with the isolation or to draw the free body diagram of the structure. So guys, we want to draw the isolation of this our beam. This beam, we isolate it like this, as a bar. This is simple supported at this point A, and it is also simple supported at point B. So the notation for simple support is like this. We have reaction at A and reaction at point B. And this our point load is at the center. We have 100 kilonewton over a distance of 3 meters. So guys, this is the free body diagram of this our structure or of this our beam. You can call it the isolation or the free body diagram. So guys, we can either call it the isolation or the free body diagram of this our beam. So this is the free body diagram of this our beam. Now we choose our orientation. I choose the positive orientation, X. And moment we rotate in this manner, I have M of X. Here I have Y. So guys, this is my orientation in which I'll be working with. Any force that acts this direction is positive. Any force that acts this direction is positive. Any force that acts this direction is negative because of my orientation. I have chosen the anti-clockwise direction. So guys, let's start. To start with the beam, we state the fundamental principle of statics, which state that sum of external forces must be equal to 0 for a body or for a structure to be in equilibrium. The sum of all the forces acting on it must be equal to 0. So guys, that is why we make this condition. Sum of external forces is equal to 0. So what are our external forces? There we have RA. This is one RA. We have plus 100 kilonewton. This is another one, and this is another one. We now have plus RB. We equate it equal to 0. Alright guys, now we move to the second step, projection. Projection on X axis. Projection on X axis means forces that act horizontally, the normal forces. Forces that act horizontally. When we look at our beam, we discover there is no horizontal force. So the projection on X axis is equal to 0. So projection on Y axis. Projection on Y axis. Projection on Y axis means the vertical forces. Projection on the Y axis means forces that act vertically. So when we take a look at our beam, we are going to discover that we have RA is a vertical force, 100 kilonewton is a vertical force, RB is a vertical force. So projection on Y axis. This is our orientation. We discover that our RA is moving in the same sense like our orientation. So we have plus RA. Now this is 100 kilonewton. It is coming down, acting opposite to the direction of our orientation. So it receives a negative sign. Same with our RB. So we have plus RB equal to 0. So we make RA and RB the subject of our equation. So RA plus RB, sorry guys, is equals to 100. It is 100 because the inverse of addition is, the inverse of subtraction is addition. So we add 100 on the both sides. We take negative 100 plus 100 is equals to 0 plus 100. That's why we have 100. You can term this one equation 1. So guys, we now go to further research. That's the sum of moment of external forces about a particular point. Let's choose point A to be our center of moment, must be equal to 0. Sum of moment of external forces about a particular point. I have chosen point A. You may choose point B, any point. But it's a secret to choose the center of moment. Choose the center of moment where many unknowns are active. Or choose the center of moment where you have many unknowns so that you'll be able to eliminate. Because the point you choose to be your center of moment, any force that acts at that point is 0, except if there exists an internal moment, it will not be 0. The internal moment will not be 0, but the forces that are acting there will be 0. Why? Because the line of action of that our force pass through the center of our moment. So guys, thank you. Let's apply the principle. We know generally that moment is the product of the force by the perpendicular distance. In other words, moment is the product of the force by the lever arm. Let's say L. So guys, let's continue. We are now going to take the moment of RA about point A. This is our center of moment, A. We said that any force that acts at our center of moment is 0. Why? Because the line of action of that force passes through our center of moment. If we extend the line of action of this our force RA, we discover it passed through this our center of moment. So the moment of RA about point A is 0. The moment of 100 kilonewton about point A. This is our direction of moment. Our moment is moving like this. And our force is coming down. Means it receives a negative sign. So negative 100. Negative 100. 100 is the force. Now we need the perpendicular distance or the lever arm. The perpendicular distance from here to here is from here to here, which is 3 meters. So into 3. And the moment of RB about point A, our moment is still rotating like this. Guys, permit me to do this so that you better understand. But as we move further, I'll no longer be doing it. So since you become a professional, so thank you guys. We discover our force is moving in the same direction as the direction of our moment. So we now have plus RB into the perpendicular distance. Because RB there is the force. Now the perpendicular distance is from our center of moment up to where we have the force. So it is 3 plus 3, which is 6 meters. Equal to 0. Now we make RB the subject of our formula. Is equal to 300 kilonewton. So guys, this is it. We made RB the subject of our formula by taking 6 times RB, give us 6 RB is equal to 300. 100 times 3 is 300. Now, the opposite of addition, that is, if we are not adding, we are subtracting. So the inverse of subtraction is addition. So we add 300 on both sides. So negative 300 plus 300 is equal to 0 plus 300. That is why if we say negative 1 plus 1 is equal to 0. So at this point, negative 300 300 plus 300 is equal to 0. So it will give us 0. That is why we are now going to be left with 6 RB is equals to 300 kilonewton. So guys, thank you very much. So let's look for our RB. We divide all through by 6. 6 here 1, 6 here 1, 6 here 1, 6 into 30. So guys, don't forget, just as I told you, you need your calculators at every moment. Let me remind you, you need your calculator at any moment when you are doing your structural analysis or load evaluation when you are solving applied mechanics. So guys, don't forget your calculator. So guys, this is my calculator. Like I told you, an engineer is known for his calculator. So thank you guys. So let's take 300 divided by 6. We are now going to have 50. So therefore, our RB is equal to 50 kilonewton. This is the value for our RB. Now, if we substitute this our RB in our equation 1, we are going to obtain our RA. Now let's make a statement. Substitute RB equals to 50 kilonewton in equation 1. So guys, we are now going to substitute this our 50 kilonewton inside this equation to obtain our RA. So we have RA plus RB equals to 100 kilonewton. This was our equation 1. So let's substitute. So our RA now is equal to 100 minus 50. So our RA is equal to 50 kilonewton. So guys, this is it. How to evaluate beam on a simple support. So guys, there's another thing we need to do. There's something we need to do. We need to evaluate the shear force and the bending moment of this our beam. We need to calculate the shear force and the bending moment of this our beam. So guys, let's go. To do the shear force and the bending moment before drawing the diagram, we use the original beam that has been given. We don't use the isolated beam or the free body diagram beam that we have drawn. We go back to the original beam and we cut after a force. We cut after a force. This is a force. We cut like this. This is a force and we cut like this. So in this our simple beam with on two simple support and a point load, we are going to have two cuttings or two shears. Two cuttings or two shears. Now, we work here with limits. We work here with limits. We work here with limit. So guys, normally in the exercise that I saw online, that I saw in a past question, here was supposed to be 3, here was supposed to be 3, and we have a length of 3 meters. Thank you guys, this is just the correction I'm just making now. Thank you very much. Now, this is our first cutting, this is our second cutting. And guys, as we saw, we are going to be using the two directions, both the left view and the right view. So guys, thank you very much. Let's start with the cuttings. Alright, first cutting. So guys, after you write first cutting, you are working with limit, with boundaries, with limit. Just as in integration, when we are integrating the integral velocity of 3x plus 4, ranging from 0 to 1. So guys, these are the limits we are working with when we are doing integration. But in cutting, we are also working with limit in zones. So guys, we are also going to use the limit notation. So guys, if from here to here is 3 meters, it starts from 0. And we are working with a distance of 3 meters. If we cut here means you are working from 0 is less than or equals to x and x is less than or equals to 3. So guys, this is our first limit we have obtained. 0 is less than or equals to x and x is less than or equals to 3. Now we draw the free body diagram of this our first cutting. We are now going to have something of this nature. Here we have the n of x. Here we have the t of x. We choose the positive orientation. And we have our m of x. So guys, here is RA. Guys, there's a critical reasoning at this point. There's a critical reasoning at this point. So please pay attention. If we cut anywhere along this beam in this our first cutting, we cannot say that we have cut a certain specific distance 1.5, a certain specific distance 1 meters, a certain specific distance 2 meters, right? So we name that distance we have cut an imaginary distance known as x. You can name it as y, name it as z, any letter of the alphabet, as far as you know what x, y, and z stands or represent to you. So guys, thank you very much. So guys, we have cut here. So we are going to represent this imaginary distance to be x. Now, our normal force, n of x, is equal to 0. Why is it equal to 0? Because there's no horizontal force acting on that beam. So our shear force, T of x, shear force means vertical forces, just as you see it represented here in my orientation. So we have plus RA is equal to 0. The reason why we are working just with RA is because RA is the only force that appears on our isolated section. So let's look for our shear force. T of x is equal to negative RA, which is equal to negative 50 kilonewton. So guys, as we move further with more complex beam, I will show you more simpler ways to analyze beams, simple supported beams and a point load, and even uniformly distributed beams. But as we are going gradually, I will teach you the more simpler ways. So guys, thank you. If you integrate your T of x, you are going to have your m of x. But guys, let's leave it for now. I will teach you when we get there, when we are mature, when we are big, when we are grown up. So thank you. Thank you very much. This is our T of x equals to negative 50 kilonewton. Let's look for our m of x. So guys, looking for the m of x, this is where your center of moment is. This is where your center of moment is applied at this extreme end. Our moment is rotating like this. And this our force is going up. So it is acting in an opposite direction to the orientation we have chosen. So it receives a negative sign. And we know that moment is the product of the force by a perpendicular distance. So this is our center of moment. This is the force. So the perpendicular distance from RA to our center of moment is this x. So we affix our x there. We equate it now equal to 0. Now, our m of x, let's look for our m of x, will be equal to, we do this man, just as, let's use the common term, people say he crossed over the equality sign. Okay, this man will cross over the equality sign and takes a plus sign, which will be 50x. Because the value that we obtained from our A was 50 times this distance, which is x. This is our m of x for the first cutting. So guys, you can take a look at it, analyze it. If there are any errors, notify me in the comment section. Please don't forget to subscribe. Don't forget to like. Don't forget, guys, to share the videos to your fellow colleagues, your fellow students that have problems in structural So guys, thank you very much. Let's move to our second cutting. This is our second cutting. Now, there is a known distance. 3. So guys, we put our 3. It's less than or equals to x and less than or equals to the total length of the beam. The total length of the beam. Since we are working with limit, we are working with boundaries. So, we are now working from 3 to 6 meters. So 3 is less than or equals to x and x is less than or equals to 6. We isolate we have 100 kilonewton. We have here our arrow A. Now guys, please pay attention. We knew from the beginning that from arrow A to our center of moment, the distance was x. So guys, if from our arrow A to our 100 kilonewton, guys, let's verify it. If from our arrow A to our 100 kilonewton, the distance is 3 meters. So I write my 3 meters. And from here to here. And from here to here is x. I want to obtain a distance from here to here. What are we going to do? Maybe we are going to take x minus 3. So the distance from here to here will be x minus 3. Is it clear? Let me take it over. If the distance from arrow A to our center of moment is x, and the distance from arrow A to 100 kilonewton is 3 meters, it means to obtain this distance, we take the total length minus this small one, which is x minus 3. And we put our orientation, n of x, positive orientation moment moves like this, m of x, and t of x. So guys, our normal force is 0 in this case. Then in other case, just let's say in triangular beams and in inclined beams, our normal force will not be 0, because we are going to use the component of the force to resolve the force. So guys, our n of x in this beam or in this exercise is equal to 0. Now our t of x, we have an A that is going upward. It is obeying the direction of our orientation. We have plus an A. 100 kilonewton is coming down, so it is opposing. So we have minus 100 kilonewton equal to 0. So let's look for our T of x or our shear force. Guys, please, I forgot. N of x means normal force, T of x means shear force, and M of x means bending moment. So guys, thank you. So it's equal to minus RA plus 100 kilonewton. So guys, this is our T of x. If you want to use values to substitute, so we say negative 50 plus 100. Like I told you, an engineer is his calculator. So negative 50 plus 100 will give us 50 kilonewton per hour T of x. If I don't want to substitute, but I prefer, guys, we leave it here for simple calculation analysis. So guys, thank you very much. Let's look for the M of x and we draw the shear force and bending moment diagram. So guys, our M of x now will be equal. Our M of x, this is where our center of moment is. Now, if our moment is rotating like this, we are this force. It is coming down while our arrow A is going up. So our arrow A receives a negative sign into the perpendicular distance from arrow A to our center of moment is x. Guys, is it okay? I believe it's okay. So let's take the moment of 100 kilonewton about this point. This is our center of moment. Our moment is rotating like this. discover our 100 kilonewton is moving in the same direction like our orientation. So it receives a plus 100 into the perpendicular distance or the lever arm from our center of moment to the force is x minus 3. So x minus 3 we equate it equal to 0. So our m of x will be equal to 50x. Guys, the reason why I put 50x is because we calculated our and A and we had 50 and multiplied by this perpendicular distance which is x, it gave us 50x. The reason why it has changed from negative to positive is because we want to look for our m of x. So all this value, as we usually say, will cross the equality sign for easy explanation and understanding. To make the job very easy, we usually say we carry everything like this and transfer over the equality sign. But mathematically and arithmetically is not correct. The statement is not correct. We don't carry everything and transfer over the equality sign. We do the opposite of what has been done on the both sides. So guys, thank you very much. So we have this minus 100. If you want to expand 100, guys, let's leave it like this, x minus 3. So guys, this is our m of x for the second cutting. So guys, we can now move ahead to draw the shear force and bending moment diagram. So guys, you can take a look at it. So guys, this is how the structural analysis being step by step, chronologically. So guys, thank you very much. Just take a look at it. So guys, we are going to clean some portion to draw our shear force and bending moment diagram. Let's clean this part. Let's clean this part since we know the value of our answer for arrow A and arrow B. Guys, it is always advisable to draw the table of values. So we say table of values. We underline. Table of value, you are drawing the limits, the zone at which we are working with. That is the number of cuttings you had so far. So we had 0 is less than equals to x, less than equals to 3, and 3 is less than equals to x, less than equals to 6. So guys, you draw a vertical line, draw a horizontal line, put it in a box like this. Guys, you see where this x is? Put a line there like this. Where this other x is, put a line like this. Put a vertical line. So guys, the first one is our t of x. Guys, sorry. Here. So here we have our t of x. Sorry guys, we are supposed to start with the n of x. The reason why I'm doing it is because you should know that n of x is included in the table of value. T of x and our m of x. So guys, let's begin. We knew from our calculation or from our analysis that theoretically we had no horizontal force, meaning no normal force. So everywhere was 0, 0, 0. For our t of x, for our first cutting, our t of x was negative 50. So since negative 50 is a constant, meaning it has no variable like the x, we simply take the constant and put in our first cutting, minus 50, minus 50. This is for the first cutting. Now you are entering the second cutting, you leave the T of X for this first cutting, you look for the T of X for the second cutting. So guys, if we do the calculation here, we are going to have negative 50 plus 100, which is 50 kilonewton, and it's a constant. So 50 kilonewton and also 50. Guys, let's come to our M of X. Our M of X for first cutting is 50x. Because our M of X for first cutting has the variable x, we are going to substitute this limit. Take this 0 and substitute where you have x. So 50, so you are going to have something like this. 50 times 0 is 0. You put 0 in this box. Substitute 3 where you have, so it will be 50 into 3. 50 times 3 is 150. So the value at this point will be 150. So guys, we are done with the first cutting. Let's enter the second cutting. This is our M of X. This is our M of X. So guys, let's do some calculation. If we have 50x minus 100x plus 300. So 50x minus 100x is negative 50x. Now plus 300. So this is our final M of X for the second cutting. So let's use these values that we obtain for our final M of X. Here guys, I simply expand this bracket by taking negative 100 times x, giving negative 100x, negative 100 times negative 3, giving positive 300. Now I like them. They are like them. So 50x minus 100x is negative 50x. Now plus this 300. So let's use this value. Substitute 3 in that. So 3 times 50, we have negative 150 plus 300. Negative 150 plus 300 is the same as 300 minus 150. So 300 minus 150 is 150. We do the same, we substitute 6. So we are now going to have 6 times 5, 30. So 300 plus 300. I have substituted 6 here. 6 times 5 is 30. And we have a negative sign, so you will now give us negative 30. We have fixed the 0 that is there. Plus 300, which will give us 0. So guys, it means here will be 0. In advanced level or when you are solving applied mechanics in your GCE, each time you solve the beam and it gives you 0 here, you hear the whole class will be shouting, beam dollar, beam dollar, beam dollar. Why? There is joy because the beam has closed. Actually, practically is true. Let me show you why it is true. You see here, it starts at 0, means it's starting at this point. It will deflect like this. Sorry, since it's a point load, it will deflect like this. The certain distance, 3 meters, 3 meters. Due to this, 100 kilonewton. So guys, it must close at this point of 0. At this point of 0. So each time you solve, your beam must give you at this point 0. So guys, as we solve further problems, I will do my best to explain in a simpler way, simpler manner for you to understand. So guys, this is a table of values that we have produced, that we have drawn. So guys, we are going to use this table of values to produce the shear force and bending moment diagram. So guys, let's erase all of this. People. just back this our beam. We can even use the isolated part. So we just see like this and like this. This is your RA, sorry, your RB. This is your RA. This is your 100 kilonewton. We can also put this line here. So guys, since our normal force is 0, no need to include it here. So we just go move ahead with our T of X, which is our shear force. We put a positive sign up, we put a negative sign down. Now, this part, the whole of this part is for our T of X. So the whole of this part is for our M of X. So we have M of X. We put our negative up, and we put our positive down. So guys, let's interchange. Let's put our positive up and our negative down. I want to, for easy identification and easy workflow. So guys, this is how they draw it. This is our RA. It is a force like this. This is our RB, and this is the 100 kilonewton. So guys, what are we going to do now? Is just to plot the points. Where are the points? These are the points. Our normal force is 0, 0, 0, all true. So we are not going to include it in our shear force and bending moment diagram. Our T of X, we have negative 50. Negative 50. So let's assume, since this is the negative part, this part below is known as negative. So let's assume here is our negative. At this point we have our negative 50. And here we have negative 50 again. Here we also have negative 50. Here. So guys, take note. You discover that in this line at the center we are going to plot 2 points. Why? Because there is below and there is above. There is below and there is above. So at this particular line we are going to plot 2 points. We have already plotted 1 point, which is negative 50. So the next point we are going to plot there. Why? Because it's at the same line of 3. 3 here, 3 here. So we are going to have 50. And this 50 now is positive. So we are going to take it up. So we have 50. And we have 50 here at this extreme end, length of 6 meters. So we have 50. And the 50 is positive. So guys, we have our 50 here. So guys, let's link it. This one will run like this. You go up this line like this. And then go like this. So we put a plus sign here, we circle. We put a negative sign here, we circle and we hash. Guys, we hash like this. We hash like this. So guys, this is the shear force diagram. This is the shear force diagram for this our point. Now let's go for the M of X. M of X will start at 0. This is the point 0. So we have here 0. So we have here 0. And we have at 3 meters we have 150 and 150. And it's positive. So we have, let's assume this is the 150. We have 150 and this is below and 150 above. And we come back to 0. We come back here to 0. We simply link the points. So it leaves here, come like this, and then come back to 0. And we have positive, and we also have positive, and we hash. So guys, we have used our table of values to plot and draw our shear force diagram and our bending moment diagram. So guys, this is the video I plan to prepare for you people today, and I prepared it deliciously. So guys, go through it, digest it. Please don't forget to like, subscribe, share, and comment in the comment section below for more videos. Thank you very much. This is the M of X, this is the T of X. If you have any question, inbox me. If you have any question, use the comment section below to put your question. Thank you very much. Don't forget to like, subscribe, and to share. Thank you.